All right, the purpose of this particular video is to give you a little bit of an insight on how to use Hess's Law and how to um, use the law to answer some targeted questions here about how to proceed with questions like this. So, if you recall from the end of the last lecture, we were given this problem: the hydrogenation of carbon to make acetylene here. And we recognized that there was a limitation. This is a reaction that would be very difficult to do, both logistically and in terms of trying to figure out how to possibly monitor the amount of energy that this would produce. But we were given a couple of equations here that do include some of the key components of the reaction that we are interested in. And so, what Hess's law does is it allows us to use equations like this to build a target equation like this, where all we have to do is monitor how we manipulate these equations. And then we just add the equations together to get this final equation. And once we do that, we can add together the enthalpies to do the same task. So, what we have to remember here then is what we talked about before with relationship to enthalpy. So, rewinding things just a little bit back in time, we talked about this idea overall that different phases of matter require different amounts of energy, but also if we change chemical reactions, that changes the value of delta H. So flipping a reaction around changes the sign. Multiplying reactions by fractions or multiplying them by coefficients will change the value of delta H by the same number as well. So with that in mind, let's take a look at this reaction equation. And what I should pick up on is I do have acetylene here, C2H2. Couple of problems with it. First of all, it's on the wrong side of the reaction. This equation has it on the reactant side. This equation has it on the product side. So that's the first problem. The second problem is that in addition to having it on the wrong side, it's also the wrong value. I only need one, but this equation gives me two. So I need to do two things. I need to flip this equation around, and I need to cut it in half. And so I'm going to make a note for myself here. I'm going to flip and cut in half, so multiply by 1/2. That's going to, flipping it around, 2CO2 and H2O are going to make C2H2 and 5/2 oxygen. Now the delta H value is going to be the opposite times 1/2. So negative gets turned into a positive. 2599.0 kilojoules divided by 2 is going to give me 1299.5. So that's the value that I'm going to work with here. That's what I'm going to end up using. Now I look at the next equation. The next one on my balance here is I've got carbon, and good news. Carbon is on the correct side of the equation. However, I need two carbons and the equation only gives me one. So I'm going to need to double this reaction. So I'm going to multiply everything by 2. When I do that, 2 carbons plus 2 oxygens give me 2 carbon dioxides. The delta H value is going to be double the original value. And so 393.5 times 2 is going to be negative 787.0 kilojoules. The third equation is actually the easiest one. I have hydrogen as a reactant, and I have hydrogen as a reactant, and they're the same value. So I don't have to do anything. I can leave this equation exactly the way that it was. And so when I go to put it all together, I'm going to rewrite this so that I have all three equations all together. I'm going to have 2 carbon dioxide and water to make acetylene, and 5 halves oxygen. The delta H for that one was positive 1299.5 kilojoules. I have 2 carbon plus 2 oxygen to make 2 carbon dioxide. The delta H value for that one was negative 787.0 kilojoules. And the last one is the one I left alone, hydrogen and 1/2 oxygen, making water. And the delta H for that one is negative 285.8 kilojoules. Now, if I put them all together, anything that is common on both sides gets canceled out. So I notice that I've got 2 carbon dioxides here and 2 on this side, so they cancel. I've got water over here and over here. It cancels. And I've got 5 halves oxygen here, which if I add 2, which is the same as 2.5. If I add this 2 plus that half, there's my 2.5 oxygens. All that's left over are the carbons, the hydrogens, and the acetylene, which is exactly what I was trying to make in the first place. Now, to get the delta H value, all that I need to do is add those three numbers together, 1299.5 plus negative 787.0 plus negative 285.8, which would give me a grand total of positive 226.7 kilojoules. So this reaction would actually require energy, not release it. Good information to know. So that's the only problem I'm going to do in this particular set. I am going to throw it now to a video from a lecture that I recorded last year. And in that one, you're going to see me walk through this particular practice problem, and I think one other. And so hopefully between these several examples, you've got a pretty good idea of how to handle any Hess's Law problem. If that's not the case, if that is in fact you want more practice or you want greater clarification, please feel free to reach out to me. But for now, I'm going to send it over to that previously recorded slide and get things going over there. So check in with you later. Thanks for your attention.
So let's do this example here together. Find the enthalpy change for the reaction below, given the following reactions and their delta H values. Now, the approach I take to this is I'm looking to play a game of matching almost. I want to find the correct substances and make sure that they match up, that they line up to the correct side of the equation. So for example, in my two equations, I only have one spot where I have PCl5, the pentachlorophosphorus here. and it's right here. Now, that phosphorus pentachloride is on the correct side of the equation. They're both on the reactant side, which is where they're supposed to be. Problem is, this reaction has one phosphorus pentachloride. The bottom reaction here has 4 of them. So I need to manipulate this equation. The manipulation I need to make is a 1/4 manipulation. Divide all the coefficients by 4 and divide the heat of reaction by 4. So this becomes a 1, this becomes a 1/4, this becomes a 10/4, which is 2.5. Now with this first equation, we might also be tempted to look at, oh wait, here's chlorine. I need chlorine on the other side of this equation. Let me flip it around. Problem is, I've already got chlorine on this side of the equation also. What I need to focus on is the phosphorus trichloride here. And in this first equation, the phosphorus trichloride is in the correct side of the equation. If I flip this around, I'll actually end up with the wrong answer. But again, I can see I've got 4 phosphorus trichlorides in this equation. I only need 1. So I'm going to need to do the same manipulation. Multiply everything by 1/4. 6/4 is 1.5. And that makes this one a 1. Now I forgot to do it for the bottom one. I need to do it for the top one as well. I need to divide those enthalpy values by 4 as well. So negative 2439 divided by 4 is negative 609.8 kilojoules. 3438 divided by 4 is 859.5 kilojoules. When I add these two equations together, I'll see that I've got a 1/4 P4 on this side and a 1/4 on that side, so they cancel. I'll also see that I've got 1.5 chlorines on the reactant side and 2.5 on the product side. So the 1.5 cancels and takes 1.5 of those with it, which is just 1. The net reaction, PCl5 in the gas phase. Everything else on the reactant side is canceled out. Is equivalent is PCl3 in the gas phase on the product side and 1 chlorine in the gas phase as well. This equation in red matches the equation I'm supposed to get. So we've done Hess's law correctly from a reaction standpoint. Now we just need to do it from an enthalpy standpoint, add together negative 609.8 plus 859.5. And I get positive 249.7 kilojoules. All right. Any questions with this example? All right, let's move forward. Here's one for you to try. Find the heat, the enthalpy change for the reaction between nitrogen and oxygen to make nitrogen dioxide using the three equations below and their delta H values. So do the same thing that we did in the first example. Match it up. Find the components of the target reaction and try to line them up number for number and see if that gets us where we need to go. We'll come back in a couple minutes and talk about the correct answer. All right, let's see how we did. So for me, what I would be looking at first is I need a nitrogen, and I can see that the first equation has the nitrogen I need with the coefficient that I need. So this one we're going to leave exactly as is. I also need oxygen. So the oxygen I need is in this third equation. There's two problems with it. First of all, it's on the wrong side. And second of all, it's the wrong coefficient. So what I need to do is I need to flip this equation to get it on the right side. And I need to multiply it by 4 to turn the 1/2 into 2. And so what I'm going to do is I'm going to rewrite this properly so that I have exactly what I need. So that's going to be 4 hydrogens in the gas phase plus 2 oxygens in the gas phase, making 4 waters in the liquid phase. And the delta H for that would be negative 43.7 times negative 4, which would be positive 174.8 kilojoules. And so now that I've rewritten it, I'm gonna mark out what was there before so that I don't accidentally use it when I combine everything. So now I've got my oxygen in the right location with the right coefficient. And then lastly, I have the 2 nitrogen dioxides. This middle equation has the nitrogen dioxide I need. It's in the right equation. It's in the right part of the equation. It has the right coefficient. So I'm going to leave it as it is. So what should happen is if I've got everything arranged, I should be able to start crossing out the things that are in common. So I can see that I've got 2 ammonia on the left-hand side and 2 on the right. So they're going to cancel out. I've got 4 waters here and 4 here. So they're going to cancel out. And I've got 7 hydrogens in the products here. And I've got 3 in equation 1 and 4 in equation 3. So 7 total to match the 7 here. So those cancel out as well. So all that is left is the nitrogen in the gas phase, the 2 oxygens in the gas phase, and the 2 nitrogen dioxides in the gas phase. For my delta H, since I've already manipulated everything, I just need to add them together. -115 plus -142.5 plus positive 174.8 would give me -82.7 kilojoules. If we're being super strict about significant figures, we will need to round that to -83. Since our first value doesn't have a decimal place. All right, any questions about this example?